let's try out a problem using our extensive knowledge of turbulent versus laminar boundary layers. Now, I'm not kidding, like laminar boundary layers, there's a lot of CFD, finite difference methods, all kinds of cool stuff you can do with those. So like, I really do want to jump into that more. And for turbulence, we still can find a lot of helpful information just from knowing skin friction coefficients. Because honestly, that's a big deal for us. We need to know that because that's where aerodynamic heating comes in. It also is a measure of our drag, and so we can figure out how drag is changing based on going from laminar to turbulent. Because like the pressure drag, like due to shock waves or what else is going on there, that doesn't matter as much for boundary layers. Boundary layer is all about our skin friction. So how much is that going to affect it? Okay. Let's see here. So make sure I do this right. Boop. I'm going to have a flat plate. Why a flat plate? You know we always do flat plates. Come on, we always do flat plates. And what we're going to do here is we're going to first do this for, we'll do this for the laminar case, and then we'll go back and we'll do it for the turbulent case. I'll show you both, okay? So this flat plate, zero angle of attack, alpha equals 0. It's at standard sea level conditions, so pressure infinity is equal to 101. I can't write. I will learn one day. I've been taking classes on writing. I'm getting better at writing A's. And my temperature is going to be 288 Kelvin. There we go. So, it is 2 meters long. Looks good. And it has an area S that's equal to 40 meters squared. This is a long flat plate. Woo! And one last thing, because we need so much information for this, is our viscosity is going to be equal to 1.7894 times 10 to the negative fifth. And that is kilograms per meter second. Perfect. Now, it says we want to find out what is the friction drag on this plate at 2 different velocities. So, question for us here is, what is our friction drag? And that is going to be at 100 meters per second, where we're definitely incompressible, and also 1,000 meters per second, where we're probably compressible. So, this is where we are. We're doing this first assuming laminar flow, okay? So we're going to make that assumption. We're going to assume laminar flow. Why? Because that's what I said. Is it really going to be laminar versus turbulent? Do an experiment. We can do a flat plate. You can figure it out then. Okay. So we'll go through this step by step, and then we'll get to it. First off, our overall, this is laminar, by the way, our overall skin friction coefficient, which we need for laminar flow. This is not the lowercase c, that is a capital C. It is 1.328 over the square root of my Reynolds number based on the full chord. That's a C there, not an X. Okay? That's a C, not an X. If you see an X, it's based on its position along the shape. If you see a C, that looks more like a tau. If you see a C, then it's based on the full chord. There we go. So, we know what the Reynolds number is, we can solve this. Now, sadly, we don't know the Reynolds number yet, so let's go ahead and calculate that. So Reynolds number base C is going to be equal to my density times my velocity times C, which in this case is not the speed of sound, that is the chord. That's the chord right there. Sorry, not speed of light. I've been teaching nuclear physics, I go back to that one. And that's all over the viscosity. We know most of these things, but we don't know our density, so we'll go ahead and calculate that too. So density is going to be equal to, just using ideal gas law right here, pressure over RT. And so that will be equal to 1.22 kilograms per meter cubed. And so that is enough to plug in here and get my Reynolds number. So this is going to be equal to 1.22 kilograms per meter cubed times my velocity. I'm going to do it for 100 meters per second first, times the chord, which is 2 meters, all over the viscosity, which is 1.7894 times 10 to the negative fifth. Okay, kilograms per meter second. So if I plug that in, what I get is that this is equal to 1.36 times 10 to the seventh. That is my Reynolds number. Woo! Now, since I have my Reynolds number, I can then just plug that straight into this equation, and I get my equation for the skin friction. So in that case, CF is going to be equal to 1.328 all over the square root of that big old number 1.36 times 10 to the seventh. And so it's a small number, but remember, it's a friction coefficient. It's not the friction itself. So it'll be 3.6 times 10 to the negative fourth. And then we can go ahead and put that into terms for drag, okay? Okay. So we have that right there. So our drag in that case is going to be equal to 1/2 rho infinity times V infinity squared S times my friction coefficient. And so if I plug that in, I get 87.8 newtons, but that is just for the top or just for the bottom. So if I want the total drag, it'll be equal to that times 2. So it'll be equal to 175.6 newtons. Okay. Now, that was because at 100 meters per second, I was actually at a Mach number of 0.29. So I was incompressible. I can do that by calculating the speed of sound and go from there. I just decided to skip that step. Okay. Now, we got the laminar, incompressible friction, but we have to then think to ourselves, okay, what happens if I'm compressible? That is most definitely going to happen when I have a velocity that is equal to 1,000 meters per second. And we can prove that pretty quickly. So let's go ahead and calculate the speed of sound and then figure out what my Mach number is. So my Mach number is going to be equal to, sorry, speed of sound, my bad, is going to be equal to the square root of gamma r t infinity, which will be equal to the square root of 1.4 times 287 times 288 Kelvin. Okay. And that comes out to be a speed of sound of 340.2 meters per second. So in this second case, my Mach number is going to be equal to my velocity divided by the speed of sound. It's equal to 1,000 over 340.2, which is equal to, I believe, 2.94. Yes, 2.94. So we are clearly compressible here. Now the equation I used earlier was only for incompressible. And so I have to then figure out where I'm going to go here. So going back way up here, you see that I have this equation. Actually, I'll go here. I'll just write down here again. So for incompressible, I have CF is equal to 1.328 over the square root of my Reynolds number. Okay. When I am compressible, I can't actually use that. So I have CF still. It's still a very similar thing. I still have the square root with the Reynolds number on the bottom. That's all good. But it's the top part that changes. So this part right here, I'll just say this right here is a function of my Mach number. And where do we get that from? Well, we can get it from, I'll give it from a particular figure you have in your textbook. And it's not perfect, but I'll go ahead and do my best to show it to you. So give me a second, I'm going to copy that, paste that in here so you can see it. Okay, so here is the figure. And these are from NASA's tech notes, so it's actually from a very fun reference. And so what it gives us is, you can see this right here is my skin friction coefficient times the square root of the Reynolds number based on the chord. And then what I have right here is, this is the incompressible model, which is simply saying, it doesn't actually ever care, what the Mach number is. But in real life, this value here is going to drop as I get to higher and higher Mach numbers. And so we're going to assume an adiabatic wall, because this makes things simpler on us. And so if I'm at a Mach number of around 3, I am somewhere like roundabouts here. And so we're just going to say that's about 1.2. Is that perfectly accurate? Well, I'm guesstimating here. But it's around 1.2. That is what I'm going to say this value is equal to. Okay, so with that, I can then go back here. So for compressible, I say, okay, well, CF times my Reynolds number is equal to 1.2. And so therefore I can then say that my skin friction coefficient is equal to 1.2 over the square root of the Reynolds number. As a note, this is still assuming it's laminar. We're still assuming it's laminar when we're doing this model. So if I then plug that in there, and make sure I don't make some horrible mistakes, we can solve things. So another issue here is we have our little model for it, but I don't know what my Reynolds number anymore because I have to change, my Reynolds number is going to increase. So Reynolds number, according to the chord, is still going to be equal to my density infinity times V infinity times the chord over mu infinity. The only thing that has changed is that this is now increased by a factor of 10. So it's going to just be equal to 10 times what I had last time. So I had 1.36 times 10 to the 7th. Where are you? Yep. So now it's going to be 1.36 times 10 to the 8th. Okay. So I plugged it in there, and I say, okay, CF, you are equal to 1.2 over the square root of 1.36 times 10 to the 8th. Does not look like a 10 at all. There we go. And so that'll be equal to 1.03 times 10 to the negative 4th. And then just like last time, I can plug in my equation for drag. So my drag force on one side is equal to 1/2 times rho infinity times V infinity squared times the planetform area times my skin friction coefficient. And it's going to be equal to 2,513 newtons. Why? Because that guy has increased by a factor of 100. Remember that, okay? The velocity was 10 times bigger, so velocity squared is now 100 times bigger. And then my drag, total drag, which is on both sides, is me having to multiply that by 2. So it's 5,026 newtons. So it's a doozy. We've got a lot more drag, but we're also going a lot faster. But it just shows you that the air is pulling on my surface, because this is only due to the viscosity of the air. This is not at all due to me pushing the air out of the way. It's only the air pressing against my surface, being dragged against my surface, pulling on it. And it has a lot of friction as it does so. But this is the laminar case. Having done this, we're now going to try it with the turbulent case and see how things change. We'll see how things change.